Hey, John here. Let's talk about the merge sort, okay? But before we do that, let's make sure that we know how to merge two arrays, all right? Let's say I've got these two arrays, A1 and A2. A1 has 3 elements, A2 has 4 elements in it. How do we do this? We start out with our favorite index numbers, and we're going to write some loops that are going to traverse these arrays. They're going to scan over them while these indices are less than their respective sizes, okay? Now, we assume that these arrays are already sorted. Notice they are, right? Numeric order, 5, 20, 35 for the left one, and 6, 30, 43, 52 for the right. So these two are arrays that have already been sorted of some arbitrary size, could even be 0 in theory, right, for this algorithm to work. And what we're going to do is just merge them, all right? So what do? We start out by creating some index pointers. Let's call them blue and black. And we write a loop whose condition is that while the blue index is less than A1n and the black index is less than A2n, all right? That's our main loop for this thing. As long as neither of these is run to the end of the array, in other words, okay? So then what does the body of the loop look like? Well, our goal is to create, let's call this one AM. All right, so I'm going to create this merged array out of those other ones, okay? Now, we'll need another index for that. Let's just make that the red one. Okay, so what do? We're starting like this. We ask, well, both of these still have stuff in them is essentially what we're asking, right? So we say, is the element at the blue index less than the element at the black index, right? Is A1 sub A1I, or whatever you want to call your variable for blue, less than A2 sub A2I, right? Okay, so is the green element less than the black one, all right? The answer is yes, because the blue one is less. Did I say green? It's blue. It's early when I record these things. Anyway, the blue one's less, therefore we copy it down to the merged array, and we advance the merged array index, okay? The merged array index is going to just simply remember where the end of the array is down here, where we put the new elements. So we don't need to really focus on that. That one's just going to move along every time we add a new one, just to get that red pen out of the way, all right? So once we've copied down the element that is less of these two, we advance the respective index, okay? So we then come back to what is going to be a loop, the top of our loop, and we're going to ask again, are both of these indices less than the respective maximum, than the respective element count of each of these two lists? And the answer is yes. So we ask again, is the blue one less than the black one? No. So this time we're going to copy the black one down, right? And then we're going to advance the black one. And of course, advance the index down here. Now we come back to the top of our loop. Is blue and black both less than the respective lengths of their arrays? Yes. So then we ask the same question we've been doing the whole time here. Is blue less than black? Yes. Therefore, we copy the blue one down and advance the blue. Are they both less than their quantities? Yes. Is blue less than black? No. Copy the black one down, okay? We're done with that. You advance the black one. Come back to the top of the loop. Is both of these indices less than their counts? Yes. Is blue less than black? Yes, it is. And we advance the blue. Now the blue one is equal to A1n. And when we come back to the top of the loop, we ask, are both of these pointers, these aren't pointers, both of these indices, are both of these indices less than the respective counts? The answer will be no. We will fall out of that main loop, okay? Now, how do we clean this up? We still have elements over here. Well, what we can do is just write two simple loops. One that says, drain all the remaining elements from the A1 and copy them into AM, the merged list. And when that's done, and it's done right away. If you think about the logic for that, you would just write a loop that says, while the blue is less than A1n, copy the elements into this merged list. Okay, well, there's none, so it doesn't do any. Then you just write the exact same loop again for the black one. While the black index is less than A2n, and it currently is, then we copy the element down to AM. So we put 43, and we advance this one. And back at the top of that loop, Is black less than A to N? Yes. Copy the element down. Advance. Is it still less than this? No, it's done. We have merged these two arrays into one larger array that itself is sorted. So as long as these two are sorted, you can just go kind of one at a time and then feed them down in here. That's the whole point of merging, okay? Let's look at another way to merge. All right, in this scenario, we're going to do the exact same thing. We're going to have the same values and everything, but we're going to just order the, we're going to store the data a little bit differently. Let's say we just have one big array called A. And inside that array, there's two sections of the array. Let's call each one a run. That have the values that we were looking at before. All right, so here's the values we had before: the 2, the 5, the 20, the 35, and then the 6, 30, 43, and a 52. Okay, so instead of having two arrays, we're going to just merge two runs in one array. Okay, and the way this could work is we could have the let's have a pointer here that's called, you know, like list 1 first, okay? We could also have one that's called what? Well, let's call this one mid. Let's call this one what? We can call this end. All right, now, I think you can see what's going to happen in here. Rather than have two physically separate arrays, we can just use one big one that has everything in it like this. Now, how is this going to work? The blue pointer would be the first element of the first array. The black pointer that we were just looking at would be this mid plus 1. Okay? Now, you know you hit the end of this first list when the blue pointer becomes greater than mid. It's a little different than last time, okay? Remember last time we used the number of elements. This time, this is actually the number of elements minus 1. So the logic in this function here would be, while the blue index is less than or equal to mid, okay? The black index would also be a little different because this has the end pointer. It doesn't have end, you know, plus 1 over here. So this will be while the black index is less than or equal to the end. But once you've done this, the task is exactly the same as you just saw before. This is just a little bit fancier way of organizing the data. And you'll see that this is actually very convenient for the merge sort to take place. All right, so here's some pseudocode that describes the merge process, okay? Array is the one big array that has the both of the lists in it, both of the runs in it, okay? Start is their index number where the first element of the first sublist exists, okay? And note specifically that start need not be 0. In my little drawing, I had it smushed up against the left. That need not be the case. It could be anywhere in that array. What is important is that the left and right sublists are smushed together, okay? So start is the index of the first element of the left sublist. Mid is the one I showed you. It's the last element in the first sublist, the last one of the left list. End is, again, the same thing I showed you, is the last element in the sublist on the right, okay? So these two sublists are smushed together, but they don't have to start at 0, all right? Keep that in mind. Start need not be 0 in this case. It can be, but it doesn't have to be. So the first thing we want to do is create a temporary array to hold our merged results, okay? And because this list could start anywhere, we have to figure out how big it is. Well, that's really end minus start plus 1, right? You got a plus 1 because the end is actually inclusive in the number of elements, right? It's the last end element index, okay? Now, to declare an array like this in a C program, you do it like this. You can put math in here for the size. In the last couple of decades, they added this to the language. So if you have arguments that are passed into some function, and this is a local variable called temp, you can put end minus start plus 1 in here. It'll work just fine. However, Don't ever expect this to work, okay? Not that we need it in this example. However, if you're going to declare an array and it doesn't have a constant in here for its size, in other words, the compiler does not know how big this thing will be when your program runs. And in this scenario, it could actually be a different size every time the function is called, okay? Then size of cannot and will not work. It shouldn't even compile, okay? So don't expect this to work. Because, again, size of is an operator that is evaluated by the compiler, not when the program is running. Okay, so, all right, so that gives you your temporary array. We create some indexes, start, mid plus 1. Obviously, in the scenario I just showed you, I is the blue pen, J is the black pen, K is your, what is this thing used for? That is the index into the temporary array, all right? What was the, the red pen for a while? In what I was showing you. So here's the main loop where I is less than or equal to mid, and J is less than or equal to end, right? Because those are inclusive now. Then we simply ask, is the element at I less than the element at J? And remember, I is the left one and J is the right one. So if the one at I is small, then copy that one into the new array and add 1 to the I index. Otherwise, grab the one from the other array. This one would be from the black pen, and increment that index. When you're done, you copied something into your temp array no matter what. Therefore, increment the index of the temp array, right? So this will run until one of the two indices exceeds the number of elements in here. And here's how you do the draining, okay, of the residual elements of whichever array has not yet been depleted, okay? So if there's anything left in the left half of the array, that was your I index, copy it into the temp, and then increment the pointers in the obvious way. When you've done with that, do the other list. Only one of these lists, by definition, could possibly have any elements in it, okay? Therefore, they both won't run. This does make sense. A very simple way to do this. When you're totally done getting everything into your temp array, you write another loop to just copy all the elements out of that temp array back into your main array. Okay, so this process requires this temporary array because it's not known a priori how many elements might come out of the left or the right sublists. So you can't really do it in place. You have to have this temporary array to hold these copies. So how then do you use this merge routine to do sorting? Well, let's look and see what's going on up here. If we have a big list like this that's unsorted, and we just chop it in half and chop it in half again and again and again and again until we've chopped it all the way down into a bunch of each run has only one element in it. Then we have this case down here where we can just start merging together all those single element runs into 2 element runs and all the 2s into 4s and so on, right? Because when you have a single element in a run, it is by definition sorted. So how then do we deal with creating how do we break all this up, keep track of what we've done, and then feed them all into the merge routine repeatedly, and cascade them all together like this? Well, we can write a surprisingly simple recursive function to do that. All right, let's call this merge sort. It takes the array of the entire sortable items. That's the top one up here in red. Okay, that's your unsorted array to start with. You get a start index number, which is the index of the first element in the list that you want to sort, or shall we say the first element in the run that you want to sort. And end is the index of the last element of the run in the list that you want to sort, okay? So what do we know? We know if there's only one element in that run, we don't need to sort it. We don't do anything. So if start is equal to end, we have it, by definition, that's one of these runs that have only one element in it, okay? So if it's less than n, then that means there's something to sort, okay? It has two or more elements in it. So what do? We need to cut it in half. So mid is start plus end over 2. Integer division will take place at that point, and find a suitable midpoint. It'll round up or down or whatever. It'll round it down, right, in integer division. So once we've cut our run in half, we sort the left half and the right half. Well, remember, the left half would be start to this new midpoint that we just calculated. And the right half would be from that midpoint on to the end of the sublist that we just calculated. Now look closely at what's going on here. Let's say this comes in here with a list that has exactly 2 elements in it, at which point start will equal end minus 1 by definition, okay? For example, this might be 5 and end would be 6 in that case. That's a 2-element list. Well, what happens if we do this, right? Start being 5 plus 6 is 11 divided by 2 and is an integer division. It'll round it down. Mid would equal 5. So when it comes down here and it says merge sort, it will pass the array. Start will still be 5, and mid is 5. What happens when we call merge sort? When start and mid here have the same value. When we call merge sort, the array is the array, start is start, and this mid value is what will become the end in that recursive call. And since they have the same value, this is false, that call will accomplish nothing and return back up again, right? So this recursive call in this example will return right away and do nothing. This one over here, what'll it do? Well, mid plus 1, since we had only 2 elements, is equal to end also, right? Therefore, again, this call will be sent down here for the right sublist that has only 1 element in it by definition. This will not be true and it will do nothing. Okay? So when merge sort is called with an array that has a run with exactly 2 elements in it, neither of these will do anything, and then we will merge those 2 elements. That's that case right here when we're jumping from this list that has 2 elements in it that need to be merged, okay? And when they're merged, they're already sorted because each one of them has only 1 element in it, okay? So that turns out to work just fine in Ducky, right? So that's how you create sort a 2-element list. Well, when would that ever happen, right? Well, that would happen after it was called to deal with this up here. Here's a 4-element list, right? So how does a 2-element list, a list with a run of 2 get created? Well, it's when you were asked to sort a list of 4 elements and it cut them in half, and each half was to be sorted, okay? So you can see the recursion taking place here is my point. So this one takes the left half, and then it does the right half, and then it merges whatever is done, okay? Now, the base case is kind of easy to see where you accomplish nothing whatsoever. The case where you have a list of 2 elements in it is easy to see because you know these 2 calls don't do anything. When you have the 4-element list or a 3-element list, and we track this thing through, what happens is when you call this merge sort, there is more to do, right? So if you have a list of 4 elements, like in here, being passed into merge sort, start is here, end is here. It decides to calculate the midpoint, gets this thing right here, cuts it in half, and calls merge sort on the left list and the right list. Well, you already know how those work, okay? When and only when those 2 sublists have been completed will then the results of these merges on these two lists will then ultimately be merged again. So that's what's shown down here, okay? So when you have 4 and you cut it in half into a pair of 2s that are cut in half to those 1s, we already walked through, and then you merge the 1s back together like this, the recursive call that was asked to sort this list here will have just seen these 2 subcalls completed and move on to execute the merge at that time. You see how that's working here? So when he cuts it in half and says merge left, all of this is done and merged. When he merges the right half, all this is done and merged, okay? And when that second one returns, he's left with these 4 elements in the array, and then he's going to call merge with start here, mid here, and end over there. And he'll himself merge these guys and store them back in the list, okay? And again, he'll return back to where he came from. So this can just go on and on and on and on. This tree can expand forever, in theory, right? This could just be the left half of an unsorted list that has a much more elements over here, right? So once you've got the base case of your recursion down, and I like to think the base case and one level above that base case, then you just simply keep going ad infinitum, all right? It shouldn't be that hard to convert this pseudocode to any language you might need to program in. Converting this to C++ would be pretty straightforward, and you could do that. I'll leave that as a test for the student and sort away. But thanks for watching. See you next time.